All right, so last time we talked about what the binomial distribution is. Let's take a look at what we're going to be expected to do with the binomial distribution. Look at how to find our mean, our standard deviation, and our probabilities and all that good stuff. First of all, our notation. P, as always, lowercase p stands for our probability of success. Q is the probability of failure, and that's just 1 minus p. N is the number of trials, and X is the number of successes. Okay, the same notation for P, Q, and X, well, for P and Q, but this time, since we have a fixed number of trials, that's going to be N, and the thing we're looking at, the thing we're concerned with the probability of is how many successes do we have within those trials. And the probability is calculated fairly easily. If you think about what these ugly symbols are, they're really not that bad. This just means the probability of having X successes is the probability of success to the power of how many successes we're talking about, times the probability of failure times the power, or not times, but to the power of the number of failures we're talking about, right? N minus X is the number of trials minus successes. That's your number of failures. So it's probability of success to the power of successes, probability of failure to the power of failures. And then NCX is really just how many different ways can we combine or can we move those successes around within the trials. So is it, if it's 2 out of 5, is it the first 2? Is it the last 2? Is it the third and the fourth? How many different ways can we move those successes around in the number of trials? We're just going to use binomial PDF in the calculator, and we have to put trials, probability, successes in that order. Our formula for mean is just N times P, the number of trials times the probability of success in each trial. And that's fairly obvious. And the number of, the standard deviation is just N times P times Q square rooted. So number of trials, probability of success, probability of failure, square root. Now let's take a look at how to do each of these. Probability for a particular couple having a kid is going to be 0.25. Just made that up. It's a genetic thing. Don't know exactly how it works. Don't really care. So for a particular couple, let's say that the probability of their kid having blue eyes, or each kid that they have, is 0.25. They plan to have 8 kids. What's the probability that exactly 4 will have blue eyes? Well, we could do it this way. We could do 0.25 to the 4th power, the probability of success to the number of successes, times the probability of failure, 0.75, also to the 4th power, because 4 out of 8 is for successes leaves 4 out of 8 for failures. And now we would just do 8C4. Or we could go straight to the calculator and use binomial PDF, and that's what we're going to do. Go second, distribute, and geometric PDF and CDF. We're at the very bottom of the list. We got to go up a little bit higher here to find binomial PDF. 8 trials, probability of success of 0.25, comma 4, tells us that about 8.65% of the time, and you should put this in your calculator too. I'm not going to spend time here doing it, but you should put this in and verify that you do get 0.0865 out of that as well. Okay, so you have 8 kids with a 25% chance for each kid. The likelihood that 4 of them exactly will have blue eyes is 8% of the time, or 0.08, depending on whether you prefer decimals or percents. What about the probability that fewer than 4, or up to and equal 4, 0, 1, 2, 3, or 4? That's the same thing, except we go with binom CDF for cumulative. 8 kids, probability of 0.25, comma 4. This will give us less than or equal to 4, and that's 97.3%. Okay, so if this was true, if you had 8 kids, or you were going to have 8 kids, and the probability of giving each one blue eyes was 0.25, then the likelihood that no more than 4 would have blue eyes is 97.3%, meaning the probability of 5 or more having blue eyes is really, really low, only about 2.7%. Now let's look at likely outcomes. That really relates very well to this. The mean is going to be the number of kids times the probability of having blue eyes, and I think this is natural. If your probability of blue eyes is 25%, that's 1 out of 4, so if you have 8 kids, it makes sense that probably the most likely number to have blue eyes would be 2. And the mean and the expected outcome are the same thing here. This is going to be the most likely outcome, or the most expected outcome. Our square root is going to be, and sorry, this was just 0.25 times 8, gave us 2. Our standard deviation is going to be 8 times 0.25 times 0.75. I'm sorry, I really did not leave much room there. And you can do this in the calculator. 8 times 0.25 times 0.75 gives us 1.22. All right, so our range of likely outcomes here, we double this, we get 2.4, subtract that from 2, and we get negative something, which we'd round up to 0. 2.4 added to 2 is going to be 4.4, which we would round towards the center of the interval. So our range of likely outcomes, right? If we have this situation where 25% chance of passing down the blue eyes, and we have 8 kids, we would expect anywhere between 0 to 4 of them to actually end up with blue eyes. And we see that that is the case. The probability that we had less than or equal to 4 came out to be 97, which is fairly close to 95, which is what we talk about when we talk about that range of likely outcomes. We will do a couple more of these with some more examples of the binomial distribution.